All right, so we just finished chapter 4. We are now talking about chapter 11, and chapter 11 is all about the properties of solutions. So chapter 4 is all about kind of the math or the composition of solutions. So now we get into properties, like what do solutions do? What kind of things do we find inside solutions? So basically, all of this is based off of a solvation or crystallization reaction. We have been talking about these the whole time in chapter 4. We just haven't been using these terms. So if something undergoes solvation, it's dissolved. That's kind of what we've been talking about. And if something undergoes crystallization, then it like precipitates out. So we've been talking about these same reactions. We just haven't been using these terms. So if you are looking at this in terms of like copper 2 chloride, if we were to write the solvation or hydration reaction for copper 2 chloride, it would look like this. And then maybe water gets put over the arrows, possibly, something to that effect. So again, we represent it as if it's a physical reaction. We don't necessarily represent it as if it's a chemical change that's occurring. And actually, it's a hot topic inside the chemistry community, whether this is a physical change or a chemical change. There are indications to argue both sides, and it's not something I tend to feel strongly about. But anyway, if you were to write it out as a reaction, that would be your solvation reaction, and then crystallization would just be flipped. It would be the ions coming back together to form the solid. And so they're just reverses of each other. And again, you could put water above the arrow if you wanted to do that. In one scenario, we have solute particles that are detaching. In the other one, we have solute particles that are colliding and reattaching. And if you have something in solution at your equilibrium point where it's at a happy point and the most solid you possibly can have has dissolved, you have some ions floating around, you have some solid left on the bottom. Really, it's a dynamic process at that point in time in the beaker. You have both processes going on. Solute particles are detaching, becoming ions. Solute particles are colliding, reattaching back onto the solid. It's a dynamic process. You just don't have a net increase either way happening. But solutions are very dynamic things. They never kind of sit and stagnate. The molecules are always moving. You always have that like motion going on inside your beaker. And so you really have both of these processes happening. Here's the catch at the bottom. You just have them happening at equal rates. And so there's no net gain of solids. There's no net gain of ions.
So in the example over on the right, the one on the bottom is crystallization and the one on the top is solvation, right?
You got it.
Okay.
Yes. Okay, just a couple terms. You probably know these terms from like society in general, but we want to go through and just kind of redefine, tweak your definitions to make sure they're fitting the chemical definitions as well. So the first one would be saturated. So if you have a solution that is saturated, it means it is at equilibrium. And undissolved solute has to be present. So if you think of like sitting in a restaurant trying to make lemonade for free with the little sugar packets sitting on the side, right? We've all done this. You squeeze the lemon in, you rip open some sugar packets, you pour it in, and you see how much sugar you can get to dissolve in your water. So if you have your little glass of water and you have dissolved all your sugar, that is not a saturated solution. In order to be a saturated solution, you have to have some undissolved solute sitting on the bottom, proving that you can't dissolve anything more into your water. Okay, so saturated means that you have the solution is holding as much solute as it possibly can hold, and there's evidence of that sitting on the bottom in the form of undissolved solute. If you add additional solute, it's not going to dissolve. It's going to fall to the bottom and join that nice little party sitting at the bottom undissolved. So that would be a saturated solution. This term solubility. So we've been talking about are salts soluble, are salts slightly soluble, are salts insoluble, right? So this measurement of solubility is actually a measurement we can make. So if you look down here, the solubility of NaCl at STP. So first thing to note is they note the temperature and pressure, because if you change temperature and pressure, you're going to change solubility. And we'll look at that a couple slides from now. All right, so at STP, 35.7 gram per 100 milliliters of water. So how is solubility communicated? Take a minute, think about this term right here that I am boxing. What is that? You can type it into Pear Deck if you want to. A lot of you guys are saying molarity, which makes my heart happy. It means you are transitioning your brain into a chemist's brain and you always think molarity. I love that. It's actually not molarity. It is density. If you said concentration, you're technically right. You just didn't take a stand on the units of concentration, right? It's density. It's grams per volume. It's mass per volume. So solubility, despite all our yearnings as a chemist, it's going to be communicated in terms of density. So grams per milliliter. So solubility is a measured amount. If we're looking at a specific volume here of our cup, if our volume is 100 milliliters, then the solubility is measured in a specific mass that we can get to dissolve in that volume. Obviously, if you're comparing a swimming pool to a glass of water, you're going to be able to get a different mass to be able to dissolve, which is why it's communicated as a ratio of mass per volume, right? But it's a specific mass. If we're talking about the solubility of sodium chloride per 100 milliliters, I can tell you that you can dissolve 35.7 grams into that glass of water. If we're talking about sugar, which is also a highly soluble substance, its solubility is going to be a different mass. So we in the past have just kind of been grouping, like highly soluble stuff is, we can get a significant amount to dissolve, right? So we've been generalizing it, but you can actually get a very specific measurement in grams per milliliter. Okay, and then we look at a couple variations of the saturated. So we can have saturated, we can have unsaturated. So unsaturated logically would be it can dissolve more. If you put more solute in, it will turn into ions and not settle at the bottom. And then we can talk about this term supersaturated. So supersaturated is maybe my favorite term to talk about this whole year. not because it's significant. It's probably the least significant vocab word we actually cover. We're going to talk about it now. We're going to talk about why it's cool. And then we're not ever going to talk about it again, unfortunately. But the concept of it is so fascinating, or maybe the application of that concept of it. So a supersaturated solution means that it contains a greater amount of solute than is needed for saturation. So let's say we're trying to make salt water and we have dissolved 35.7 grams into our cup. Well, if I supersaturate the solution, what that means is I can put another packet of salt in and it will actually turn into ions instead of settling to the bottom. Now, this only happens under very specific conditions, as you might expect, because if it happened all the time, it would just adjust our solubility, right? So it only happens under very specific conditions. And one of those conditions is certain molecules tend to do this. Certain molecules can supersaturate much more easily than other molecules. It's actually extremely difficult to get salt to supersaturate. Extremely difficult to impossible. Sodium acetate, on the other hand, does this fairly easily, quite readily. So sodium acetate, you can get the solution to dissolve more than it'll dissolve past its saturation point. In order to get it to do this, however, you have to play with the temperature. So like I said, if you raise the temperature, you can change the solubility. And this we see in sugar really easily, right? If you have a cold glass of water versus a boiling pot of water on the stove, one of those you're going to be able to dissolve more sugar into, right? You can get more sugar to dissolve into the boiling pot of water on the stove than you can into the cold glass of water sitting on your tabletop. If you want to make simple syrup, which is a cup of water per cup of sugar, you got to dissolve it into the boiling water first. You're never going to be able to get that to dissolve into ice water. So with a supersaturated solution, we actually raise the temperature and get things to dissolve. We get that higher amount of that higher mass to dissolve. And then when we lower the temperature back down, the solubility should lower. So in the case of salt or sugar, if we get a lot of sugar to dissolve and then we lower the temperature back down, what happens? Has anyone ever done this before? What'll happen is crystals form. So like think rock candy, right? You get a ton of sugar to dissolve. You put a string in there and then you lower the temperature back down. Well, all that excess sugar it like clumps onto that string and it comes out of solution because you have lowered the solubility, right? Well, sodium acetate doesn't do this. Sodium acetate, you lower the temperature, and as long as you're pretty careful with it, it'll actually stay in solution, and then you have a super saturated solution. Now, it's beyond its solubility point, which makes it very unstable. So if you think potential energy, you have just raised the potential energy through the roof, right? And there's certain triggers that'll make it come back out of solution. And so there's actually kind of cool videos. Let me show you one of them that shows exactly this. Wait for it. Oh, okay. Let me find my PowerPoint again. There we go. Okay, so that is supersaturated sodium acetate. So again, it's just really unstable once you lower the temperature back down because it's holding too much solute. It's over the given quantity of solvent at that temperature. That would be a supersaturated solution. Like I said, probably one of my favorite concepts, probably the least practical concept that we cover all year, but it's just so cool. Okay. I think I saw a couple questions come up in chat. Okay, so the concept of equilibrium, we can revisit this just a little bit. We're going to have a whole chapter on equilibrium down the road. But essentially what it is when a reaction has hit a point where the forward rate and the reverse rate are equal. And so you can think of copper 2 chloride. Let's think of a crystal of copper 2 chloride. So, okay, so this is how our crystal starts. And then slowly but surely, we put this crystal into water. And what happens is the water molecules are going to run into the copper chloride molecules. And the copper chloride molecules are going to show an attraction to that water, right? And they're going to break off. So instead of being part of the crystal now, they're going to break off. And so this happens, and that's what we call solvation, right? This thing is dissolving, or we might call it hydration. Water is kind of attacking these little molecules of copper chloride, and then they break off and float around the solution as the ions that they are, right? They break off into copper and to chloride ions, copper into chloride ions, copper into chloride ions. So this is solvation. Copper chloride is turning into copper ions and 2 chloride ions that are now floating separately around. Well, at some point in time, this solution is going to get so saturated with copper and chloride ions that the copper and the chloride ions start running into each other and reforming. So instead of being separate, they might reform onto the crystal. As they run into each other, they're going to reform. And so what we have happening there is the opposite. We have copper and chloride turning back into copper 2 chloride ion. And when the rates are equal, when ions are hitting and rejoining the solid at the same rate that solid is being broken apart and floating around, that is the point at equilibrium. And a really good analogy of this is if you think of a bridge, okay, and on one side of the bridge is, I don't know, Grand Island, maybe, because we're all going to Heiser Pumpkin Patch. And on the other side of the bridge is mainland. I don't know. What do we call that? Salem? It's not quite Salem, but you guys get the idea. Okay, so let's say it's 8 a.m. in the morning. All these little cars are driving and they all want to go to Heiser Pumpkin Patch, right? So they're all going to start driving down and we get this influx into Grand Island, right? So we get cars that are going from Salem into Grand Island. And then, but eventually, people go to the pumpkin patch and then they're done and they want to come back home. So eventually we get this influx of cars that's coming back, right? We get people going from Grand Island into Salem. Well, when the rate of cars coming in is equal to the rate of cars leaving, we get no net gain of people on Grand Island, right? At first, at 8 a.m. in the morning, when there were 2 people living on Grand Island, which is probably more than that, cars started going in and the population started going up of Grand Island. Well, eventually cars also start leaving. And then we get this place where the rate in is equal to the rate out. So we get this stabilized population. That is equilibrium. The forward rate is equal to the reverse rate, and that is equilibrium. And that happens with cars going across a bridge. That happens with solutions, copper chloride that's dissolving into ions. That happens with acids and bases reacting. This forward and reverse reaction rate is established in almost every reaction. We call it equilibrium. We just don't talk about it until AP chemistry because it's kind of this abstract concept that's hard to imagine. And so we really don't introduce it until you have this solid foundation of chemistry topics. Does that kind of help? Okay. Okay, so we've gone through the terms. Now let's talk through the factors affecting solubility. So as you're sitting here talking about, is something soluble? Is something insoluble? Is it slightly soluble? These are the factors that are going to determine the solubility of a compound. What's the solvent? Is the solvent water? Is the solvent hexane? Is the solvent oil? Is the solvent isopropyl alcohol? The nature of the solvent is going to have an impact. What's the solute? Is the solute copper 2 chloride? Is it sugar? Is it wax? That's going to have an effect on how soluble something is also. What's the temperature? We looked at this before. Are you dissolving something into a glass of water with ice floating at the top? Are you dissolving something into boiling water that's sitting on the stove? The temperature is going to have an effect on how much you can dissolve in. What's the pressure? So we really haven't talked about pressure a whole lot up to this point in time, but pressure also has an effect. So crash course on pressure. Pressure is the amount of force on a specific area. So how much force is on a specific area? When we talk about pressure, the one example that really helps you kind of wrap your mind around what pressure is if you think about standing on ice with your feet versus standing on ice with ice skates, right? Oh, that person doesn't look too stable. Okay, so if you're standing on ice with shoes, then you have a very specific area, which is the bottom of your shoe, that's standing on ice. And that area of so the force pushing downward is your body weight. And then the area that the force is pushing on is the spot, the footprint of your shoe, right? So if you're standing with shoes on ice, not much is going to happen. It's going to be slippery. That's what's going to happen, right? But if you put ice skates on, all of a sudden that footprint that your shoe takes up becomes a razor blade. So you still have the exact same force. The force down is your body weight, but the area over which you're exerting that force becomes really, really small. And it becomes so small, so that's the pressure. The pressure increases because the area has decreased. You actually melt the ice instantaneously, which is why you glide on an ice skate and you don't glide on shoes, right? You shuffle on shoes. On an ice on an ice skate, you glide. Because you have so much pressure pushing down on that ice that the minute that the metal touches the ice, you melt the ice. And then that little blade of water reduces the friction and you glide gracefully over the ice, right? It doesn't happen with your shoe because the area is too big, so the pressure is too small. So pressure is this force exerted over a specific area. When we talk about pressure in terms of chemistry, we think of, instead of like a foot affecting the ice, we think of molecules bouncing off of a specific area. And the molecules exert a force. So if we have 1,000 molecules bouncing off a specific area versus 10 molecules bouncing off a specific area, the pressure is going to be different, right? We can actually break glass by increasing the pressure behind that glass, right? That's why you don't want to put a cap on a glass bottle and put it in the microwave, because the microwave is going to heat up those molecules. They're going to go faster and they're going to hit the side of the molecule faster, right? And more often. So if you have, something inside a glass that's at room temperature and the molecules are hitting the sides of the glass 1,000,000 times a minute, and then you heat it up in the microwave and the molecules start hitting the sides of the glass like 9 billion times a minute, well, that amount of pressure has changed inside the glass and you're going to break the glass. So for us, pressure has to do with the amount of times molecules collide with a specific area. So pressure can affect solubility also. And then there's this fifth factor, which is this movement towards disorder, that also affects solubility. But we're going to talk about disorder when we talk about like thermodynamics. So we'll get there. We're not going to talk about it in this chapter. In this chapter, really, we're going to focus on the top 3. Sometimes we'll include pressure in that. But what's the solvent? What's the solute? What's the temperature? And then sometimes we'll reference pressure also. We'll talk more about pressure when we go through gases and we actually break pressure down a little bit in terms of gases. Okay. So if we kind of focus in on this solute-solvent interaction, what we come to in looking at solute and solvent and will they interact, this we look at in terms of polarity. So polar versus nonpolar, and how do those molecules affect each other? Now, we looked at this a little bit last chapter. In chapter 4, we found out that, something that's polar, like water, that has a partial negative and a partial positive side, this is going to affect both ions, right? It's also going to affect other things with a dipole. So other molecules that have a partially positive and a partial negative end, these are going to have interactions with each other also. So polar things tend to attract ions and other polar things. And in the same way, nonpolar things affect nonpolar things. So this obviously is going to have a huge impact on solubility of things, because if we try to put something polar, like sugar, into something nonpolar, like oil, those two are not going to show any attraction towards each other. And so you're going to have no solubility there, right? Your solvent matters, your solute matters. And most of the time we look at this in terms of polarity. Now there is another way we can look at this, which is in terms of lattice energy. And we'll get there once we kind of cover a couple more basic concepts first. Okay, one more note I want to make on solution formation it deals with the energies of solution formation. So a lot of times when we look at a process that's occurring, we talk about it as if it's occurring in one step, but oftentimes it occurs in multiple steps. And by breaking down these steps, it gives us a clear idea of why some of these processes happen. So a lot of this comes down to this term called enthalpy. And enthalpy, what we can take it to mean for now is heat. So the enthalpy of formation would be the changes in heat as a reaction is proceeding forward. Now we'll look at enthalpy in greater detail when we talk about our thermodynamics chapter, which is chapter 6. We'll also look at enthalpy of reactions in greater detail when we look at bonding in the bonding chapters. But for now, let me give you just a really brief intro. So, the enthalpy or the heat changes that occur over a whole process can be added together to give you the total heat change for that process. And sometimes this total heat change gives us an indication of why the process occurs. We can look at two different processes here. So, for example, this first one, this is like a potential energy graph. So up here would be high potential energy. Down here would be low potential energy. Okay, so here's where our reactants start on potential energy. So this arrow here is showing you the energy or the heat required to separate things. So if we think of like NaCl, first of all, the Na and the Cl have to be pulled apart from each other. That's breaking a bond, an ionic bond. So heat has to be put in to break that bond. And then the Na and the Cl separate from each other are at a very high potential energy until they interact with the water. And then that's this arrow right here. And notice that arrow is pointing in the opposite direction because when the Na and the Cl interact with the water, that actually lowers the energy. Energy gets released and it forms this much more stable compound that is at a lower energy level. So this green arrow here is kind of the net energy change. And because more energy is given off in the stabilizing steps than is actually put into the system, we would call this an exothermic or an exogonic reaction. Energy is given off. And these reactions tend to happen more than the opposite process. You can look at B over here. This would be oil and water mixing. So if you take oil and water and you separate them from their own thing, so oil separated from oil, water separated from water, and then you mix them together, notice that the oil and the water don't actually stabilize each other very much. So you get this very small change in energy. Overall, the reaction takes more energy than is given off. We would call that an endothermic reaction or an endergonic reaction. And these reactions tend not to happen. A couple other factors that can tell you if something is going to happen or not would be something that takes a process that takes a lot of energy, even if the net result is a release of energy, those tend not to happen also. Okay, so we have this idea of the heat changing through a reaction of these things kind of forming or these solutions forming or not forming. But the guiding principle always goes back to like dissolves like. So when you go into your book problems and they're asking you what's more likely to dissolve this thing, well, it's the molecules that are more like each other. If it's a polar molecule, the thing that's going to dissolve it the best is a polar solvent. If it's a non-polar solute, the thing that's going to dissolve it the best is a non-polar solute. And so we have to start looking at the structure and what kind of atoms are involved and what their electronegativities are in order to determine what kind of things will dissolve other kind of things. So take a look at the practice in your book and then bring questions to class, and we can kind of go over some of the details through all of this. Okay, so here we get into pressure effects, and this we kind of talked about before, the dynamic equilibrium, the rate of entrance versus the rate of escape. So I'll cover a couple more of these chapters in our recorded asynchronous time, and hopefully we'll get far enough through the definitions that tomorrow in class we can do some practice together. So we haven't covered a whole lot of the applied math concepts, but we have covered a couple of the concepts in the book already. So you can start to look at the questions in the back of the book. I've posted the questions on Classroom, which ones you should do. There's a couple review questions early on, like 13, 15, 17. But then they basically start in 35 when they talk about solution composition. And these are very much like puzzle type questions where they're asking you to convert between a couple different definitions of composition. Like, can you convert between density, molarity? Can you convert between a couple of these different definitions of concentration? So if you want to take a look at that today, go ahead and take a look at that. But approach it like a puzzle, like Sudoku, right? You're not going to have a clear path right from the beginning. You're going to have to play with it a little bit. And we'll do a couple practice problems like this in class tomorrow also. All right. Good job getting through some of the basic material for this chapter today.